All right, we're going to continue with our next presentation. This is Scott Laurel Roberts. It's math and musical, pitch class.
Well, hello everyone. My name is Caleb Scott Alons. I am here from Oral Roberts University. I'm a mathematics and biblical literature major. And I have two things that I love in life. I love music and I love mathematics. And so I combine that in this project. So I present to you the pitch class integer theorem. Mathematical music theory has assumed, without proof, that musical notes can be associated with the equivalence classes of groups of integers mod n. So we can test the triviality of this assertion, which we call the pitch class integer theorem, or just PKIT. And since the existing literature assumes that the PKIT without proof, the mathematical language to rigorously treat the PKIT does not yet exist. We axiomatically construct an abstract study of harmony to generalize its fundamental tenets, and to show that the PKIT is proven by this construction. We ultimately verify the PKIT to support the existing mathematical models of music theory. And so what does this realistically look like? Research in music in terms of mathematics has often gone in a direction where music has music theory, and then mathematicians look at what exists in music theory, and then develops a model in mathematics to describe what's going on. And so I argue that the opposite case is actually more appropriate, that we should take mathematics to inform how we describe music theory. That is, what we have in music theory is a result of mathematical structures. And so axiomatic harmony, what we'll do is just refer to this term as the study in mathematics that seeks to axiomatize musical harmony to go in the direction of mathematics informing what we have in music. Here we have, over on the left side with the C equals 0 and the stack, this was Thomas M. Fior. He proposed this pitch class integer model first, and in order there was Thomas M. Fior, followed then by Otto Song, who then proposed independently another pitch class integer model. That is, we can put the integers together with musical notes to describe what goes on in music theory. A few other people independently developed the idea as well. We had Christy Kennedy and David Wright just about the same time, around 2008, reaching the same kind of conclusion. And then there was a journal article that was published about 4 or 5 years ago by Sock, Gelton, and another author in a journal that essentially summarized, and that's what's on the bottom left, is the group of integers. They synthesized what Fior wrote and with what Song wrote, essentially claiming that these pitch class integer models can simply be turned into group theory. Now the issue is that there has been no proof of this pitch class integer model. In other words, the papers that have been written and the research that's been done starts with the base assumption that we are allowed to make this correspondence between the musical notes and the integers, and that is what I've contested. So we're going to construct a tuning theory from a lower level base assumption so that we can construct and then ultimately prove that this model is indeed correct. And so instead of going from the base assumption that the pitch class integer model in itself is true, we'll make a much more fundamental assumption. And that assumption is simply this: sound waves exist. And that's a really difficult assumption to contest with concern. You have to hear me say that with sound waves. And so what we do is we simply say pitch, okay? We're going to have positive real numbers that are corresponding to frequencies that are given in hertz. And then because we're talking about positive real numbers, pretty much all of the wonderful mathematical properties that already come with the reals immediately apply to what we have in pitches. And so then we develop this idea of an octave as an interval of pitches. And the proposition that we have here is not going to be really used to prove other lemmas and theorems, but rather the proposition simply says that what this kind of definition for describing what we have in pitches and frequencies is going to cover all of the possible sound frequencies that can exist. In other words, this will in fact close what exists in current modern music theory. When we have musical systems, when you play music, what you do, raise your hand if you actually play piano or any sort of musical instrument. You know that you're not interacting with the full infinite number of pitches that are possible. There's a fixed set of pitches that you have, and so what we do is there's some sort of a selection process that goes on. So we generalize this using the tuning set. In other words, we're selecting n distinct pitches given in every single octave to distinguish from the infinite number of pitches that can exist in the positive reals. And when we do that, we also know that we have things called scales. We have relationships between the musical pitches that we have. And so we formalize this and generalize it out to this idea of steps in step sense. And that is, a step is going to be this rule that says, okay, if I want to get from one pitch to the next pitch, I'm going to call that a step. It's going to be some sort of a map that takes a pitch inside of the tuning set into another pitch in the tuning set, and then we can take the collection of all the rules that govern how I get from one pitch to the next. And if you play piano, if you're classically trained or something like that, then what we understand is we have two kinds of steps that we assume. We have the half step that we assume, which would take you, say, from C to C sharp to D sharp, etc., or the whole steps that we can assume. So that would be C to D, etc. This is a more general picture that's going to strip away that assumption that we have imposed from Western musical harmony onto the way we've done our mathematical models. And so here's just a few examples to give you an idea. Abstractly, this is a third octave. Say we decide to pitch, take 4 pitches for every single octave, and we can see that we can describe the relationship of all the pitches in any given octave by this idea of a step. So we've given this selection of pitches some structure. And then here's actual computations. If I decided to then generally say I want a tuning set, I want 5 pitches in every single octave given by this particular relationship. Then if I set an initial pitch to be 100 hertz, then what you see on the graph is actually the exact computations that the construction is going to generate in the set of positive reals for frequencies in hertz. And so you can plug all of these frequencies into a sound generator and it would produce essentially what tuning you have on those octaves. Here's another one, and this is the power of this particular definition, is because what we have in Western harmony is very restrictive. And so we're used to having uniform step ideas. The step doesn't need to be uniform per se. It's just any kind of rule that takes you from one pitch to the next. So this is a very non-uniform step set example. But yet again, we can see we can still compute pitches given some initial conditions. So here we start everything, we make our computations based off of the frequency of 500 hertz, and we can generate what pitches would exist inside of those octaves. And so naturally, these ideas go together. We have tuning sets together with the step rules that are going to be combined. And what that's going to give us is we just call that the tuning space. And then the tuning space will be different from what we've been doing in the previous examples, because we need to specifically specify, okay, at some point I made an arbitrary decision. And that arbitrary decision was, what am I going to tune everything to? And so that's what we're going to call the sigma, essentially the standard pitch. Have you ever been to like a classical orchestra symphony concert or something, where at the very beginning, the very first thing that they're going to do, conductor comes out, and then the oboe is going to play A 440 hertz, to which the entire rest of the symphony is going to tune to. And then in addition to that, sometimes they'll actually do, and depending on where you're at, they will give what they call a concert B flat. In other words, the horns will then tune to a different standard pitch from which their instruments are then calibrated to. And so this idea of, okay, I can take my selected pitches and then choose an arbitrary pitch to then tune the rest and choose the rest of the pitches I'm going to use in harmony. This is so far the furthest generalization of tuning that we have in music theory. And so depending on whether or not your steps are all going to be uniform or not, that's the difference between what we have by chromatic and non-chromatic. And I say chromatic as an allusion and a nod to the existing musical harmony, where chromatic scales that are currently understood in our Western tuning systems is going to be the case where you have a uniform step. And that uniform step is n-tone equal temperament. Most people have heard of 12-tone equal temperament if they've studied music or tuning. If you have a piano at your home, this is exactly what your piano tuner is doing. He is tuning all of the pitches to these frequencies in hertz on the keys. So it's given by a very specific pitch formula. And then here we have T12. In other words, we're going to do most of our music, all of the music you've really interacted with, is going to be, we split the octave into 12 parts. And then what we do is we say, okay, in those 12 parts, I want the relationship of the steps to be this idea of equal temperament. And on top of that, we tune all of the rest of the pitches around this, of the frequency 440 hertz. And so here, this is a viola. And a viola is a stringed instrument that we can calibrate to really any frequency, but the most common frequency given in Western harmony is A is 440 hertz. And that is given because that is how we build the highest string on a viola. So that is 440 hertz. And so what I did was I wanted to show and verify that these definitions actually mean something and aren't nonsensical and contradict every single thing that we've been doing in music theory for the last bajillion years. And so what I did was I did a very, very tedious, kind of horrible work of typing out all of the pitch calculations that go into the frequencies. And if you were to put these all into a pitch generator, this is giving, in order, the following pitches. That is generated from our definition of the tuning space from equal temperament tuned to specifically 440 hertz. And when you take pitch formulas that go in other octaves, you can then generate the other pitches that are going to exist, and then from that, where you create music. There's this other tuning space that's sometimes used. This is more in electronic production or approximations and computer programs of end-tone equal temperament, because if we're comparing these kinds of irrational, 12th roots of numbers versus just simply linear ideas, it's going to be a linear idea in every single octave, that's going to be easier for a computer to handle. So depending on the precision that you want in your tuning, this is going to be more practical in terms of can your ear pick up the difference between 5 or 7 hertz given a specific pitch. And that comes down to human imprecision, but not necessarily a mathematical difference. So what we do is we need to move away from the pitches into this idea of musical notes. Because most time when you think of music, you think of the musical notes, and I've been saying pitches, pitches, pitches. And so what's the difference? And so when we have this idea of octave equivalence, I'm going to play for you 2 different pitches. So this is the and our human ear recognizes all 3 of those things as essentially musically the same. Right? We decide that those are somehow equivalent. But I just played 3 completely different frequencies. So those 3 separate frequencies in hertz are very different, but yet we've decided to classify them as the same. And so there's a very specific relationship. That is, they happen to be the endpoints of the octaves that we defined in the beginning. That is, the frequency is going to be some multiple of doubles of the frequencies. And so we can have other relationships. That is, this frequency, they're separate frequencies. They're all different frequencies in hertz, but yet we've decided musically to categorize them as the same thing. This is octave equivalence. So this idea that we're going to define an equivalence relation on the pitches being the same number of steps away from the bottom of how we define the octave partition. We can prove that it is in fact an equivalence relation, and given the way that we have our definitions, the equivalence relation properties essentially follow immediately from equality relations. And this proposition, we don't really use it to prove anything else, but I felt like I needed to include it because this essentially justifies how we can compute the rest of the pitches in every single given musical note. That is, given any frequency in a tuning space, there is a valid way that you can generate by formula the rest of the pitches. And so I can then know that all of the are related and then are related and are related, etc., etc. This formula is the reason why, if you were giving this to a computer, it could do that for you. And it's proven to be correct, which is good, because I need this to be consistent with what already exists in music theory. So, we have the notes, which are the equivalence classes that then result from applying an equivalence relation on essentially a set. So if you have a set of things, you say, I've got an equivalence relation, there's a natural partition that's going to form. And so all of those equivalence classes, or we're going to call those the notes, that's the difference between a musical note versus the pitch. In other words, all of the separate pitches are contained in the same musical note. So what we mean by the musical note A isn't just a single pitch. That musical note A contains all of the frequencies in hertz, essentially, that we've decided to categorize as being related to what we mean by that pitch, and then we call that A. The names of the musical notes are, of course, a nod to what already exists in musical harmony. But, technically speaking, there are an infinite number of ways we can define musical notes that we technically don't have the notation for yet in Western musical harmony. And so this lemma we're going to use to just prove some results later, but essentially says, again, those endpoint and equivalence classes have to be the same because they're related by definition back when we were defining what the tuning set was. And so here again, this is the 12-tone equal temperament. That's what we can play on musical instruments, classical music, even pop music, pretty much every single genre of music that's popularized in Western culture and even sometimes in the East, tuned to 440 hertz. The one thing that has changed is that 440 hertz. we call it pitch inflation. I don't know if for some of the more musical ones of you know what that is. In other words, A used to be tuned to something lower. That frequency has climbed from about 415 hertz all the way up to 440 hertz over the last 80 or so years. And so it wasn't really fixed until about 1980, and the American Standard Association said, okay, enough, let's just stop it right here. 440 hertz is going to be what we mean by that standard pitch of A. And so now we can relabel what the work that Zong already did in the pitch class integer model, but now we can actually represent it in what's going on in terms of the construction of musical notes as being equivalence classes that are being represented as the sets of all of the pitches that relate to the musical notations here in this table. And again, we call these notes chromatic because that rule given by equal temperament is their uniform steps. And so here, again, we can now formalize the musical notes that we know well in here. So when you go to a concert and the oboe is playing their 440 hertz, that is concert A. And then everybody tunes from that. And the way that they then tune from that is from concert A, they take the fifth below, and those four relationships between the pitches is into how the string section is going to tune himself. And then there's usually a B flat sometimes given for brass. And then middle C on a viola is actually just the very, very center of its sound. And that pitch, which is one octave below 440 hertz, and it is in the note C. So the notation really highlights that these musical notations should not be seen as themselves the pitches or the elements, but rather they contain all of the pitches that we then classify through octave equivalent as being part of those musical notes. And so then the tuning note simply is containing whatever we have the standard pitch in. So whatever the standard pitch is going to then generate the equivalence class that is the tuning note. We need to move this toward algebra now, because again, the pitch class integer model at the beginning was saying that we can relate the musical notes to groups of integers. And so now that we actually have a concept of what musical note really is with respect to the construction from pitches, we can start building toward that. So these two lemmas are going to be used in other proofs. Essentially, they're really small results, but they're really necessary hardware. In other words, if I take a specific note, and then I take the step up from that note, that's the same thing as taking the step up from all of the pitches inside of that equivalence class. And so that's going to result, by definition of the step, in the next set of pitches that are then all one step above, which is going to be considered the next note. So that's why I can say we can go to C sharp. That's essentially applying that step rule uniformly across all of what we mean by C, and that's going to result in all the pitches that we then call C sharp. And then any given note can be expressed in terms of the bottom of the octave. In this case, we're going to be more interested in the note that is related to the tuning note. So we can relate all of the notes in a system to the tuning note, and then collect all the notes together, call it a note set. And so then the note set, in this case for 12 tone equal temperament, is just this standard A sharp, B, etc. And then trivially, we have that the note set, there's going to be n notes for every single note set. We define an operation called harmonic addition. Essentially, what we're going to do is we're going to say, if I add two notes together, that's going to be the same thing as if I take the pitches and then add their overall indices. In other words, how much we've shifted by how many steps we've taken from the same starting location and resulting in a new pitch. So the only really nuance in having to prove that this is actually closed is in the event where the sum of x and y, those indices, exceeds n. In that case, you could actually rewrite the inequality using the lemmas that we had proven before to shift it over, and now you have a new number, x plus y minus n, that is contained under n minus 1, which satisfies definitionally the restriction for what it means to be in the note set. So we do have closure in all cases with all combinations of notes. Together, we prove it's a group, it's associative, we have identity. The identity is nu k 0, and the inverses for nu k are nu k n minus a. And so this group then, if we call that the harmony group. The harmony group of n notes, hn, is essentially the note set, and then we have that together with harmonic addition. And so that now, we finally have the language to actually talk about the pitch class integers here with more rigor. Essentially, I could say, okay, what I really mean by we can associate these integers with the elements of groups of integers, I'm saying I have a group, the harmony group specifically, where the musical notes are then related with this particular operation, and then now we just want to show that these two groups are isomorphic to each other. they're isomorphic to each other, then the pitch class integer model stands. It's true. So all we got to do is show that phi, which takes hn to integers mod n, is a bijective homomorphism. And so given phi, which is nu kx to x, that is going to be injective almost definitionally. And then for every single integer z that's going to be in the group of integers, you can just find the node that is nu k z in the harmony group, and that'll map over, so we're on to as well. And then the homomorphism is given as shown. And so the pitch class integer theorem is indeed verified, and it is true. That is the paper. So I want to acknowledge the Lord. Glory be to God the Father Almighty. Glory be to Jesus Christ, his one and only Son. And glory be to the Holy Spirit, the giver of life. In Jesus' name. I'd also like to thank Dr. Lang, my advisor. Through the Oral Roberts University Stanley White Foundation, I was able to do this research with help with some of their funding. Also, Dr. Elizabeth Carlson, a good friend. We talked a lot of math. She's also a musician. And then also my friend Daniel Hansen from the Biblical Studies side of things. So, any questions?